Hello everyone, myself Yadagiri, Assistant Professor, Department of Electrical and Electronic Engineering and also the Faculty of Basic Electrical Engineering. So in this session, we are going to discuss about the series and parallel connection of the resistors. So here we need to discuss about the numerical or one example based on the series and parallel combination, that we can say network reduction technique. So based on network reduction technique, we need to find the required parameter. Means the circuit mentioned to get the current given by the battery or current given by the source. So we need to use the technique is a network reduction technique. Network reduction means we need to reduce the complexity of circuit. That means need to arrange the whole circuit with the series and parallel combination. So by reducing that, we'll get the equivalent value across the source. So that is the question given. So here, how can you get the total current of circuit means? First of all, we need to know the formula. We know the formula of the circuit, that is current value of the circuit, that is a V by R. According to Ohm's law, I equal to V by R formula we can use. So V by R means if it is only the one element present in the network, we can apply directly V by R. But here we have the network is a bigger network, so that the total current of this network equal to the total voltage upon R equivalent. Total voltage upon the R equivalent. So from this formula, the unknown thing is the R equivalent. So the total voltage already given as a 12 volts. The R equivalent is we don't know, because we have the different connection like series parallel combinations are there. So that we need to get that value as a equivalent value. So we need to find out the R equivalent of the circuit. So for that, the source, assume the current direction. So wherever we heard the word as R equivalent in any kind of circuit, so we should know about the series and parallel combination of the elements. So then only we will easily get the equivalent distance value, because we already know about the series and parallel kinds of connection of the different resistance. So different elements or different resistors are contained in series. The equivalent value should be addition of them. So different elements are arranged in parallel. The combination of the multiplication of those two elements upon the total distance of those two elements, that is a parallel connection equivalent value. So based on that, the current given by the source as a I total. So the current given by this kind of source is a I total. The same current moving to this point. Here also I total only. And then the current is divided between these 2 points. So why should I take this current flow or current circulation means? So we need to identify the series and parallel combination of the elements. For that, we need to run this current towards the entire network. Based on the current division and based on the current flow of the network, we can identify the series and parallel combination of the elements. So based on that, the current enter here and divide between these two, because these are in parallel. That's why the current should divide, so that these two are parallel, we can conclude. And the remaining current, this current enter here and divide between these two. And whatever the current through the 10 ohm resistor also circulating, then moving towards this point and end by this point. The whole connection. So here the 10 ohms, 20 ohms and 10 ohms are in series, means there is no current divisor. So based on the current flow of the network, so we can identify simply the series and parallel combination of the elements in that. So the last branch, the 10 ohm and 20 ohm 10 ohm branch, so there is no current dividing. That's why there is no current division taken place between these two elements first. Then also the 10 ohm also connection in series with the 20, and also there is no current division among the 3 elements. So based on that, 10 ohm, 20 ohm, 10 ohms are in series, and the whole combination is parallel to 40 ohm resistor. And after that, so which in series to 12 ohm resistor, and after that which also series to 8 ohm resistor, and whole combination is parallel to 40 ohm resistor. So based on this analogy, we can get the equivalent distance value. So whenever or wherever we heard the word as equivalent distance value, we need to identify the series and parallel combination of the elements, that is based on the current flow, or also we can say based on the connection. Here I am going to take the based on the current circulation. So by that, we need to identify the series and parallel combination of the elements. So here we need to get the R equivalent based on that one. So here we need to approach the series and parallel combination identification from the starting to ending. and we need to reduce the complexity. I mean the series and parallel combination reduction happening from the ending towards the starting. This is the method. So for that here the 10 ohms, then comma 20 ohms, and also one more 10 ohms are 10 ohms are in series. I mean connected in series. So these three elements are connected in series. So the equivalent of this combination, you can say this combination, so that is R equivalent of the above combination is so we can say 40 ohms. So this combination is the 40 ohms, and after that we need to redraw the network because we got the reduction in the complexity. So that we need to redraw the network as a 40 here and 20 here, 8 ohm we got. So instead of this whole thing, so we can simply redraw it as this is the 12 ohm and this is the 40 ohm. So instead of the 3 we can draw the 1 element as that is also 40 ohms. Again same analogy based on the series and parallel connection. Based on the series and connection, series and parallel connection, so these two are in parallel. Again current is circulating towards this element. So because the current given by 12 volts battery is this one, so again divide between these two and also enter here and divide between these two. So these two, in these two combination the current should be again divided, so that these 40 and 40s are in parallel. So the equivalent of this combination is simply we can use the R by N method, that is R by N equal to that R is the corresponding resistance value, that is a 40, and the number of resistors we can take it as a N, that is a 2. If the combination we got it as a equal values, so that we can use the R by N formula, so that we will get the R equivalent as so 20 ohms. Otherwise also we can use the other method to get the equivalent value, that is a R equivalent of above combination is a R1 into R2 upon R1 plus R2 equal to the previous method. So that is a 40 into 40 upon then that is 80. So both are gets cancelled. Here are 2 4s and also the 2 2s, and also here 10 we got finally 20 only. Here also we got 20 and here also we got 21, same only. So this is a shortcut technique to use the parallel connection to get the equivalent value of that combination. And after that also we can redraw the network. Same here 12 volts battery key capacities, here 20 ohms, and this is the 40 ohms. Now this is the 8 ohm resistor, so this is a 12 and this one is a we got 20. Same only here. So from this one, so here from this one, these three elements are in series and which parallel to 40 ohm resistor. So these are 12 ohm we forgot to take. The R equivalent of this combination is again 8 plus 20 plus 12 we can get. So which means here 40 we got directly. So the entire network should be like this, that is 12 volts, this is the 20 and this 40 left as it is, draw as it is, and instead of the 3 we can directly draw the again this 40. So here 20 ohm resistor. So what we want to find from this one means total current of the network. So need to find out the total current of network. So by using the network reduction technique, so we need to get the expression so like this. So here the whole R equivalent of the above combination. Why? Because the network got it like a simple. So the current is enter here and divide between these two. So based on this one, these two elements are parallel and which in series to 20 ohm resistor. So therefore the R equivalent of whole combination is here 40 parallel to 40. So which series to 20. So like that we can write here according to the R by N method we got 40 by 2. So plus 20 key capacities. 20 here also plus 20. So therefore R equivalent of the entire network should be 40 ohms. So this is the way to get the equivalent resistance value of the different circuits. So is it enough to get more? No, means we need to find out the total current value. The question asked the current of the circuit, I mean current circulation by the voltage source. So that is the I total equal to V total by R equivalent. So therefore I total equal to the 12 upon the 40. So this is the overall current after simplification of this one. This is a 6 and 20. This is the 6, then 20 we can take. Therefore I total equal to 3 upon 10. I mean 0.3 ampere given by the voltage source. I mean the total current circulation by the voltage source is how much? It is a 0.3 ampere. So this is only, so we need to find by using the network reduction technique. So we have reduced the network complexity. That's why it's called network reduction technique. Based on this one, we got the current value is a 0.3 ampere. So this is the end of this question, and we need to move to the simple one more question. So that is, so the network mentioned below to get the equivalent resistance of the above network. I mean equivalent resistance of the given network. So again, so wherever we heard the word as equivalent resistance value, wherever the word we need to heard that the equivalent resistance value, that is, so we need to identify the first of all series and parallel combination of the circuit from the starting onwards. I mean from the starting towards the ending. I mean the starting of circuit. So from this point to here we need to identify the series and parallel combination of the elements. So that is under the base of the current flow of the network, or also the based on the different element connection. So the easiest way to identify the series and parallel connection, we need to connect a dummy source. If it is not available, we need to connect a dummy source. So this is a dummy voltage source. So this dummy voltage source delivers some current. So this current enter towards the 4 ohm resistor. Here the current entering at the 4 ohm resistor is this point. I mean this current is entered to the 4 ohm resistor. The same amount of current, there is no division. So enter here and divide between these 2 points. Divide between these 2 points. And whatever the current enter through the 6 ohm resistor, that is here, that's so going to come and so leave from this open terminal, I mean this N terminal, and the remaining currents are only circulating. So then the 3 ohm current enter here and divide between these 2. So based on this one, so the 4 ohm current again move towards the entire branch, that is 4 and 5 3 ohm resistor. So among these 3 resistors, there is no current division taken place. That's why 4 ohm, 5 ohm and 3 ohms are in series. So in the entire connection, so here 4 ohm, 5 ohm, 3 ohms are in series, which parallel to 4 ohm resistor, and the combination is in series to 3 ohm resistor, and which parallel to 6 ohm resistor, and which is in series to 4 and 3 resistor. So this is the way to identify the series and parallel combination of the resistances based on the current flow. So here this is the way to identify the series and parallel combination of elements from the starting to ending, I mean from starting towards the ending. So here based on this, we need to get the reduction of the circuit, I mean to get the equivalent resistance between the required terminals. So we would like to take the equivalent value from the ending towards the endings towards the starting. So from starting to ending, we need to apply some current or some dummy source that delivers some current. So based on the circulation of current, we need to identify the series and parallel combination from starting to ending. So after the identification, then we need to reduce the complexity of circuit from the ending to the starting. So this is the way. So based on this one, the 3 ohm resistor, then 5 ohm and also 4 ohm resistors are in series. So which parallel to which connection is parallel to 4 ohm resistor. I mean these 3 elements are in series, and which is parallel to this 4 ohm resistor. So the R equivalent of above combination is we can write the 4 parallel to, then 4 plus, then 5 plus, then 7. So here we got 4 parallel to, so here 9, then 16. So R equivalent of this combination is so 4 into 16 upon then 4 plus 16. So this is the equivalent of only this combination. So the R equivalent is, so here 64 upon 20. So here 2 tens and two twos. So here we got 2.2 ohms. Yeah, 2.2 ohms. Then we need to read the network with the reduction branches. So here we need to change the color of the pen, and so we can take the equivalent resistance value is here 4 ohms, 6 ohms, also 3 ohms. Keep as it is. This is the 4, this is the 6, and this is the here 3 ohm. So this one is 2.2 we can take, because we got the resultant as a 2.2 only. So at these 2 points only we need to get the R equivalent value, effective resistance of these two combination. This is the 3 ohm. So in this connection, the again need to assign a dummy source to identify the series and parallel combination of the elements. So that is here the current given by the dummy source as this one. So based on that, the current enter here and divide between these two. It's a simple circuit only. So these two are in series and there is no current division, and which parallel to this one. So therefore the remaining network should be like this, and only we got like this. Here the upcoming network is going to come like this. So for this we need to get the reduction of these two combinations. We need to find out the combination of these two. That is R equivalent of this combination is 6 is parallel to 3 plus 2.2. 6 is parallel to 3 plus 2.2. That means 6 parallel to, then it is a 5.22. It's 11.22. So divide by here 11.22 is a denominator. So based on this one, it is a 6 into 5.22 upon here a 6 plus 5.22 means we got like that is so 11.22. So same we can replace here 30, then so 31.8 ohms here we got as a resultant one, divided by 11.22, and here 3 ohms and here 4 ohms. So the effective resistance of the above combination is 4 plus, so 31.8 upon 11.22 plus 3 ohms. So whatever the resultant value we got, that is the answer for this question. So this is again network reduction technique to get the equivalent distance between the required terminals. So this is the end of the problem, and we need to summarize the entire session. So the summary of the session means here till now we have discussed about the series and parallel connection. So what does it mean by series connection, and what does it mean by parallel connection? So in the series connection, if any resistances are contained in series, so the equivalent of them is the addition of that magnitude values. Means the two elements are contained in series, the effective resistance should be R1 plus R2. So coming to the parallel connection, so two elements are arranged in parallel like this. So this is the one element and also the other element. This is the R1 and R2. So based on the parallel connection, the effective resistance based on the proof, that value is a R1 into R2 upon then R1 plus R2. So this is the series and parallel connection. And after that also we have gone through the current and voltage division rule. So the VDR, we can say voltage division rule, is applicable for series circuits to determine the voltage across the individual elements without applying the other circuit principles like Kirchhoff laws, Ohm's law, like that. So again to this one, the voltage through the particular elements. So this is the given elements as R1 and R2. So this is the applied voltage as a V. We can take it as a V. So the voltage across the first element equal to the, again to the VDR, voltage division rule, V1 equal to, so total voltage of circuit into same resistance upon total resistance of the circuit. Whatever the element to determine the voltage value, that corresponding resistance is the same resistance value. So that is the voltage division rule. Now coming to CDR, and also we have discussed about the current to division rule. The current division rule is applicable for parallel circuits or parallel network to determine the current through the individual resistances without applying again any Kirchhoff laws and also the other fundamentals. So let us say this is the circuit we have. So this is the R1 value, then this is the R2 value. The total current of circuit is I total. Now this one is the I1 R1. I mean the current through this one is I2. The corresponding element is R2. So we need to get the current through this current division rule. That is I2 means I2 equal to, so total current of circuit into again opposite resistance. So previously we taken the same resistance. Here we need to take opposite resistance of this particular element. That is R1 divided by R1 plus R2. So this is the I2 value by using the current division rules. So in this whole session till now we have discussed about the series and parallel connection of the different resistor, and also how do we get the effective resistance of those connection, and also we have discussed about the voltage division rule and also the current division rule. How can you use the voltage division rule and also how can you use the current division rule? So we have discussed in this session. So this is the end of the session. Thank you. So see you in the next video. In the next session we need to discuss about the network theorems, that is the superposition theorem, and also the remaining Thevenin's, Norton's and maximum power transfer theorem. So thank you. Thanks for watching.